Let's start this section with an empty slide. Well, so far I explained multiple access schemes that require some kind of coordination. Someone has to assign parts of the spectrum to certain users, or someone has to assign time slots, frequencies, whatever. But what happens if you cannot coordinate anything? So let's assume just some islands somewhere, different islands, and assume you have a mountain here, a large one, etc., etc., and you have, let's say, some computing resources here, maybe an antenna there, and then you have distributed over the islands some more, let's say, part of a campus, for example, from a university, and you all want to access the main computer, for example. Then somehow you have to send your data over the air. The problem is you cannot coordinate the points in time when the different users from the different islands, A, B, C, D, start sending. You simply do not know it. So you have to find out a kind of an uncoordinated way of medium access. In this case, accessing the central facility, accessing the central antenna. And one scheme, how you can do this, has a name that remembers a bit of this setting. Well, maybe you know it. It's called Aloha. Okay, so now we are on Hawaii. The Aloha scheme, the very simple one, also used in wired systems, well, is quite simple. You have different senders A, B, C, and if the senders want to send something, they just start sending. Very simple. This is basically no coordination at all. Okay, so, but isn't this a horrible scheme? It depends. It depends on the current load you have. If there's not that much going on in your network, it's fine, because you have low latency, you just start sending. Low overhead, well, you send and that's it. And a low probability of collisions because of the low load. But if you have a high load on the network, the scheme simply fails. So, the Aloha scheme is a random distributed scheme, and it's a time multiplexing. Same channel, that means the same frequencies, and you simply start sending, and as soon as two signals from different senders reach the receiver at the same time, you have a collision. You can improve the scheme. Then we have so-called slotted Aloha. That means you time synchronize the senders. So that means you send a clock to all the senders so that all senders are synchronized in time, and you can start sending only exactly at the start of a time slot, for example. So sending must start at slot boundaries. So slotted Aloha is still a simple scheme, but has a higher performance compared to Aloha, depending on the traffic load, the traffic pattern. And it's quite funny to see that even in today's mobile phone networks, we still see the Aloha, the slotted Aloha scheme for certain channels. Classical GSM, GPRS, UMTS schemes, they use slotted Aloha for the so-called random access channel. The random access channel is the channel where the devices initially try to access the medium. No coordination, because the base station actually does not know when a mobile phone wants to send something. This is completely uncoordinated but synchronized. So all mobile phones are synchronized, So they get their clock from the base station, they are synchronized, so they know when they're allowed to access this random access channel. But the random access channel itself, it's completely uncoordinated. So if you have, for example, many time slots, we will learn a bit more about this, then there might be a time slot for the random access channel. And this is exactly the time slot where different mobile phones are allowed to access the medium in a completely uncoordinated way to ask for certain, well, resources, frequencies at the base station before they set up a connection and can transmit user data. So the random access channel is also the channel that is heavily overloaded. For example, New Year's Eve at the Brandenburg Gate, when thousands, tens of thousands of users want to call someone, want to send a message or whatever. And then those devices, the mobile phones, have to access the random access channel, the RAC, this random access channel, or the packet random access channel, depending on the technology. UMTS, again, you have a random access channel combining packet and circuit switch data, etc., etc. But all these technologies have this random access channel, and all the devices compete for this random access channel. And if you do not have any additional coordination, well, slotted Aloha is the best you can do. I mean, if there's no coordination, what can you do? You do not know anything about the participants. You do not know anything about when they want to send something. So all you can do is at least time synchronize them, but then it's slotted Aloha and you will have collisions. So in case of overload situations, for example, the mobile phone network will simply block certain percentage of the users in a kind of a random fashion, or a certain percentage of the packet data, etc. So simple schemes, but limited performance. Still the best you can do if you do not know anything about your devices. The efficiency for these schemes is pretty low. Well, assuming a certain distribution for the packet arrival, packet length, etc. If you look up literature, it says always something like 18% for Aloha, 36% for slotted Aloha. That means if you go higher with the load, you have more and more collisions until the whole system is blocked. So you cannot go up to 100%. So under certain assumptions, 18% for Aloha, 36% for slotted Aloha. That's not that high. So this is why most of the systems require some coordination. And what do? They perform certain reservation of resources. With the help of reservation, you can increase the efficiencies up to more, depending again on the traffic pattern, traffic load, something like 80%, for example. You cannot go up to 100% with normal traffic loads in wireless systems. As we will learn when it comes to wireless LANs, Wi-Fi systems, there's a lot of overhead always associated with wireless systems. So the basic idea is, if you're a sender and you want to send now, you signal some system, for example the base station, oh, I want to reserve a future time slot. So the idea there is that you say, okay, I have to send. I do not start sending now, but I send in the future, and please give me certain resources. And as soon as some coordinator gives me some resources, I can use the resource without collision. That's the idea. The reservation requests. That's my reservation request. There we can still have collisions. Okay, but what do we win? Now we are back. Same situation as we had with slotted Aloha. We can have collisions. Well, the trick is the reservation requests are only short packets. There might be a collision, yes, but the statistical chance for a collision is way lower compared to the longer data packets. So, as soon as you're successful with your reservation request, you have a guaranteed time to send your longer data packet. That's the idea. Well, the problem is reservation causes higher delays. Compared to Aloha or slotted Aloha, you cannot simply start sending your user data. First you have to ask, may I send? And if someone tells you yes, you're allowed to send, then you can send. Remember, that's like students in the lecture hall, well, I have a question, and then you actually tell the students, now you're allowed to send, then the student can ask something. But this results in a higher delay. And this scheme is very well known since the 60s of last century, for example, for satellite links. Okay, so in satellite links also you have the Earth, and then you have your ground stations, and somewhere up there in the sky you have your satellite. So the ground stations are uncoordinated. They want to send something, so they send their reservation request up to the satellite, and then the satellite on the downlink grants access or blocks access or whatever. And if I get access, then I finally can send a lot of data. That's the idea. I will just give you some examples because they are more or less blueprints for many other schemes you will see in mobile phone networks, in wireless LANs, etc. But remember, the basic idea is back from the 60s in satellite networks. So one is an explicit reservation, one is an implicit reservation, and then also some other Reservation-TDMA schemes. So what is the basic idea? All these reservation schemes come in two phases. So first of all, and that's shown here with these tiny slots, we use, for example, a Aloha or slotted Aloha scheme. So that's first mode. First mode is an Aloha scheme. This is exactly where we compete. There's competition. We have small reservation slots. There we might have some collisions. So we actually can get a random number, and then the sender says, okay, I tried in slot number 3, or I tried in slot number 5, or whatever. The collisions will happen at the receiver side, which is the satellite, for example. Okay, that means I have my ground station somewhere, satellite dishes, satellite up there. So in this phase 1, we try to make a reservation. It can be a collision, but the collision happens up there at the satellite. If there's a collision, then the satellite, well, will actually tell the ground stations unsuccessful attempt from whoever. But if one of the station is successful, then the station is allowed to access a time slot in whatever frame that will follow. Be aware this example is not, well, don't take it 100% in time, so there is some more time, so in between one goes up to the satellite, then the satellite sends a reservation list down. That's important. The satellite sends to all the ground stations a reservation list, and after that the stations are allowed to access the time slots. So you perform some reservation in these tiny slots for future frames. So for example, the yellow station was successful here and reserved the future frames. But in between this phase 1 and the phase 2, the satellite, not shown here, has to send on the downlink kind of a reservation list, a list of successful reservations. And then all ground stations know, okay, who's allowed to send data in which time slot. That's the idea. And in those reserved time slots, there should be no collisions because all the ground stations got the reservation list and that's it. There are no collisions there. So that's like you call up a restaurant, make a reservation for a table. There could be a collision while you make the reservation. So if the restaurant has several phone lines, but as soon as someone told you, okay, successful reservation, the table is yours for next week or whatever. It's important that all stations are, well, consistent in the list at any point in time, the list of reservations. They all have to be synchronized, but synchronization can be done from the satellite down to all the ground stations. So there's no coordination between the ground stations. So no cable between the ground stations. Okay, if we had a cable, why using the satellite? Okay. So that's an explicit reservation. So in one phase, you make a reservation for a future frame explicitly. That's one thing. But you can also perform a so-called implicit reservation. Implicit reservation, that means that as soon as you occupy a certain time slot within a frame, you can always use this time slot in all future frames. Okay, how does it work? So first of all, in this figure, you see time frames. Frame 1, 2, 3, etc. Each time frame consists of 8 time slots. I want to reserve a time slot within a frame. And the frames repeat and repeat and repeat. The idea now is, let's look at slot number 1. As soon as you successfully made a reservation for time slot 1, you can stay in this time slot and transmit your data. That's a good idea for longer transmissions, like a TV broadcast, like an interview duration 30 minutes or whatever. Not really for bursty traffic, but for, well, this kind of longer transmissions of something. So, okay, as soon as we have a time slot, we can stay there. That's idea number 1. Idea number 2. As soon as, for example, time slot 3, I end using a time slot. So D uses time slot number 3 in frame 1, but then stops using the time slot. Stations can compete for this time slot. Okay, how is this done? How is this competition done? Because remember, we have here many ground stations somewhere here with the satellite dishes. We have the satellite up here. Okay, so now it's important to have a look at this reservation list. The reservation list is sent from the satellite to all the ground stations on the downlink. So that's the way how the satellite synchronizes all those ground stations. So you always have a time slot in the uplink within a frame, and you have a reservation list or reservation vector on the downlink. And you see, this is this alternating pattern. You get a reservation list on the downlink and you have a frame in the uplink. This can be done in a FDD scheme on different frequencies. So this runs in parallel. Okay, so now let's have a look on the reservation list before we come back to how do we get a time slot. on the reservation list, the satellite tells now for our time slot number 3, D occupies this. Okay, D. But also, the satellite cannot actually foresee when D stops sending. This is why the satellite says, okay, D occupies this time slot number 3, and then D stops sending. Here, I mark this time slot. D suddenly stops sending. Okay, then the satellite recognizes, oh, D stopped sending. That means after frame 2, that means in my next reservation list, look here, there is no one using time slot number 3. Okay. Now all the other ground stations are happy because now they can start competing for this time slot. Okay? So they compete, try to access, and this is a mean example, a collision happens at the satellite. None of the ground station recognizes this collision but the satellite. So, okay, how does now the satellite tell the ground stations that there was a collision? Well, the satellite again signals in the reservation list, no one was successful. And again, all the ground stations who want to transmit, well, maybe there's also some kind of statistical distribution, some random process here. Now, they all want to transmit compete now again. In this example, let's assume only E wants to send something. Maybe the others took another time slot. Now, how does the satellite signal that E was successful? All the stations now see, look at time slot 3. E is now the owner of time slot 3. Now everyone knows from this point onwards only E is allowed to transmit something in this time slot. So the same can also happen without any collisions. Just have a look at time slot 2 or time slot 8. Time slot 8F stops sending. That means the satellite signals to the others, okay, you can compete for this, and now D is successful and D enters this. So that's the basic idea. So depending on the traffic patterns, sooner or later someone will enter the time slots. So this is an implicit reservation. So no one explicitly makes a reservation, but as soon as the satellite signals that there's an empty time slot, the ground stations may compete for this time slot, and then the satellite again signals the competing stations if the competition was successful for one of the ground stations or not. So that's another scheme. A third one, just to give you an example. We can do even better with this reservation. Now you already learned that these two phases might be a good idea. So why not having a certain mini slot phase again, and then a longer slot with potentially guarantees? That's the idea. Now in this scenario, each of these mini slots, and this is where the competition happens, each of the mini slots actually reflects a reservation for a certain number of data slots. And as you can see, the system can be used with different settings of data slots. The length of the data slots might be different number of bytes, etc. And with this scheme, we can make again reservations by competing for these mini slots. That's one way. That's one idea. Or, and this is the example shown here, every station has its own mini slot. So as you see, you can adapt the schemes. So there's not only this or that scheme, they all have their pros and cons. Now let's assume each station has its own mini slot. So station 1, 2, etc. up to station 6 in this case. 6 stations. Each station belongs to one mini slot. And now I can make a reservation. In this example, station 1 and station 2 made reservations. Maybe station 3 did not make any reservations. The point now is, if you made a reservation, you're allowed to use the data slots exclusively. Without reservation, well, best effort traffic could fill the empty slots. So if the other stations recognize, oh, no one made a reservation, for example, for here, this part of my TDMA frame, then best effort traffic could fill this, and you could also do this for empty slots within these parts that belong to certain stations. So these examples should just give you some hints of how you can design these more coordinated schemes. What is important to remember is, we can have two phases. A short phase with competition and a longer phase without competition. Or, as shown here, a short phase where I make reservation, and then a longer phase where I can maybe fill in gaps with best effort traffic. And then there are many, many more different schemes. Okay, so these are, let's say, some kind of fundamental ideas. Now let's come back to a quite concrete problem. A concrete problem of our wireless LANs. The Wi-Fi systems, they suffer from the effects I explained in the last sections called hidden and exposed terminals. What can we do there? To avoid the problems, we introduce the MACA scheme, multiple access with collision avoidance. And here you exactly see the two phases. Phase 1, we use short signaling packets. And these packets, those short packets, these packets, they can collide. I will show you the scheme using figures again, similar to the ones I showed you already when I introduced hidden exposed terminals. But interesting here is now we introduce two new packets, a so-called RTS, request to send, and a clear to send, CTS. RTS, that means a sender requests the right to send from a receiver. And the packet is short. That's important. A short packet compared to the longer data packets. And then there's a CTS, a clear to send packet. This is used for the receiver grants the right to send as soon as the receiver is ready to receive. And those very short packets, they contain a sender address, a receiver address, and a packet size. So we know actually who sends the packet, who is the receiver, so from sender to receiver. And the packet size is important. The packet size will tell us for how long do we need the medium. So how long do we actually block the medium? This is important for all the other stations because if they know the packet size and the data rate, they know now I have to be silent for the next 300 something microseconds, for example. And you will find this scheme in the classical standard IEEE 802.11, our wireless LAN, and it's called a distributed foundation wireless MAC. Distributed because wireless LAN do not have a kind of a central controller like mobile phone networks. There you have the base station, you will learn this, base station controller, and they control the network. Not for wireless LANs. For wireless LANs, no one actually controls the network in the classical wireless LAN. So all stations are equal. Yes, you have an access point connecting your wireless LAN to your DSL router, for example. But the access point actually does not control the medium access for the classical schemes. So how does it work now? The MACA, collision avoidance. Let's go back to our problems. Our problems of hidden and exposed terminals. So first of all, hidden terminals. The problem was A wants to send something to B. C does not notice that A wants to send something, also send something. Then we have collision at B. So what do we want to do? Now with MACA, same setting. Both A and C want to send something to B. But now we send first of all short packets. What happens if both send the short packets at the same time? Collision. Okay. So, where's the advantage? RTS, CTS, both are short packets. So statistically, it's very seldom that you have collisions there. And the point is, if one sender is the first one, and there's no collisions with the CTS, then the receiver B sends back a CTS. Well, what does it mean, sending back? We have this kind of omnidirectional antenna, so we distribute, we broadcast the CTS. And that means C also receives the CTS. What does C now know? C learns, and that's what we learn out of the CTS. Some A, never heard of, but some A wants to send something to B. I'm outside the transmission range of A, but I learn also, well, I'm within the transmission range of B, assuming symmetric links. If the links are asymmetric, the scheme has a problem. So if you have highly fluctuating links, highly asymmetric links, especially if you have mobile terminals, then you might run into problems even with a MACA scheme. Now let's assume symmetric links. Then C learns some A wants to send something to B. I can hear B. Okay. So that's a problem. I should not send, because if I now send something, there will be collision at B. Plus I learn the duration, this and that, whatever, milliseconds. That means for C, please stay silent for the next whatever milliseconds. And then I can sense the carrier again. So this is a way of solving the problem of hidden terminals, because now A is not hidden anymore. Because C learned there is some A, and I might cause problems if I start sending. And vice versa, C is also not hidden for A. But MACA also helps avoiding the problem of exposed terminals. Exposed terminal, that was the situation where C wants to send something to whatever, a D. Okay, to be honest, D has to be inside the transmission range, so long antenna here. So C wants to send something to D, and B wants to send something to A. Now the problem was that if C performs carrier sensing, because of the transmission range and the broadcast character of B, C will receive the signals from B and refrains from sending. That means exposed. So C is exposed to B. How does MACA help? Well, B starts sending RTS, broadcasting the RTS. So C learns B, I receive B, and B wants to send something to A. Fine, I don't care. So what? I want to send something to D. What else does C learn? C will not receive the CTS. And this tells terminal C that it cannot hear A. That also means I don't have to wait for it. I mean, if I cannot hear A, assuming symmetric links, then my signal to D will not interfere and cause collisions at A. That's the idea. I want to avoid collisions at the receiver, so that means at A. And because I cannot receive A cannot receive me, and I can start sending to D. Yes, there are collisions here, but that doesn't matter because we are interested in the collisions at the receiver. So B signal is still strong enough at the receiver and C signal will add to the noise. I don't care. So that's the idea. So MACA helps also in case of exposed terminals, and this means it can increase the performance in both cases. This scheme, RTS-CTS, is an optional scheme in the classical wireless LANs, and sometimes depending on the driver or whatever, you could switch on this scheme. Sometimes it's called, well, RTS-CTS, sometimes it's only called, in case of heavy interference, try this. There are also many drawbacks of these schemes, but that's just a very basic scheme that tries to avoid the problem of hidden and exposed terminals. What else can we do when we come to wireless and medium access? We can do something very simple. Polling. Okay. If we have a very kind of a central terminal that can be heard by all others, like the teacher in the classroom, this base station, whatever, can poll the other terminals. That means ask the students, do you have to send something? Do you have to send something? Do you have to send something? Or poll only some of these other terminals. So that is a very, very old scheme known from the typical mainframe terminal scenarios. But you can use this polling. Interestingly enough, a polling scheme is used, for example, in the classical Bluetooth. Bluetooth uses polling. We will learn there's a master, and this master polls the slaves. And slaves are not allowed to send anything without the master. So, polling. You can do many different schemes of polling. Look up in the literature, there are many schemes. For example, randomly addressed polling. So that, for example, the terminals, it's interesting scheme, terminals send a random number with the help of whatever other scheme. We will learn how CDMA works, or you can actually send this random number using other multiplexing technology, like whatever students show random numbers. This could be, for example, our scheme. And then I create, as a teacher, a list of these random numbers, list of terminal numbers, whatever. And then I pick one of the terminals, one of the students, and we have a collision. If randomly, this can happen, two students or two terminals pick the same random number. So that's one of the ideas. And so then you can actually go through this list and then ask all the terminals on the list, and they can send something, and then we can start with this random scheme again. Just to give you some ideas how you can also do this. So polling is another scheme. That's also a classical scheme in USB adapters. Then there are also some more fancy schemes. You don't have to be expert in all the schemes, just to show you different schemes. Researchers, scientists came up with different schemes. The 60s, 70s, 80s, last century. Another scheme is that you actually signal the state of our medium with a busy tone and a downlink, and you signal with a special special signal called busy tone that the medium is occupied or the medium is idle, and you're not allowed to send if the medium is occupied or busy. And as soon as this busy tone stops, you can start accessing the medium. Well, and then there might be successful transmissions, there might be collisions, and with the help of acknowledgements, a scheme you know from computer networks, you can signal if the transmission was successful or not. So the medium access itself is not coordinated, but as soon as basically this busy tone stops, you can access the medium. So this is implicitly done in a lecture hall. The busy tone is you hear someone else talking, and then as soon as everyone stops talking, you may access the medium. But think of in a wireless setting, the devices do not necessarily hear each other. So you cannot directly apply the same scheme from the classroom. So this is why we use this busy tone, for example. So I, as a teacher, could raise a red flag indicating now I am busy, and a white flag, for example, you're allowed to access the medium. This is a classical scheme for packet data transfer in CDPD in the US system AMPS. Okay, now you learned a bit more about schemes, how you can access the medium using usually TDMA, time multiplexing, because that's easier to handle compared to frequency. We can combine this, but please go back and look up the problem of hidden exposed terminals. What happens in the case of hidden terminals and exposed terminals if we use Aloha, slotted Aloha, reservation Aloha, or MACA? Compare what happens there, and you will see, oh, we will run into some problems there. Then think of different traffic patterns, different scenarios with fixed data rates or varying data rates. What are the advantages if we use a fixed time multiplexing pattern compared to a random or demand-driven time multiplexing? Compare efficiency. And then if you compare this, I guess you might come up with the answer why traditional mobile phone systems rather use fixed multiplexing patterns, but the classical computer networks use more random, demand-driven patterns. And today, in our mobile phone networks, we have more and more computer-generated data. So, how has this changed our mobile phone systems? What are the problems? How do we adapt? Think back again, what are benefits of reservation schemes? Think of the two phases. How can we avoid the collisions during data transmissions? Why is the probability of collisions now with the reservations lower compared to classical Aloha? What are the disadvantages? Then think back of MACA. I mentioned some problems. How can MACA still fail? Well, it was made for the problems of hidden exposed terminals, but it can fail. Think of mobile stations, changing transmission characteristics. Maybe the links are not that ideal.